Hello students, today we are going to discuss about basics of liquid state. Before going to liquid state directly, we can first discuss about different states of matter. What is the state of matter mean? State of matter is one of the distinct forms in which matter can exist. As we all know, the three fundamental states of matter includes solid, liquid and gas. In the solid state, the particles of matter are packed tightly and are under constant vibratory motion, that is a periodic back and forth motion. Vibration of solids are very small and hence solid possesses very less kinetic energy. Due to the locked in position of the particles, solids are not compressible and hence are rigid. Solids are of definite shape and volume. To make change in its shape and volume, an external force is required. Most solids that we encounter oftentimes are crystalline in nature. These are salt, sugar, minerals and diamonds. At room temperature, wood, metal and rock, etc. are also solids. When heat energy is provided to solids, they melt and convert into liquid. Constituent particles in the liquid state of matter are loosely packed compared to that of solids. These particles can flow around easily and have more kinetic energy than solids. Liquids have definite volume but indefinite shape. When kept in a container, liquid conforms to its shape. When a solid rock is heated up, it starts to liquefy and is converted into molten lava. As we all know, water at room temperature is liquid. Have you ever wondered why gas is a fundamental state of matter? Particles of gases have high kinetic energy. Gases have an indefinite shape as well as volume and assumes the shape and volume of the container. Gases have a lot of interparticle spaces and hence gases are highly compressible. This feature helps in the convenient transportation of gases. Liquefied petroleum gas, that is LPG, used in home for cooking, compressed natural gas CNG used in vehicles, oxygen gas used in hospitals are compressed in cylinder for convenient storage and transportation. Apart from these three states of matter, there is a fourth state of matter known as plasma state. Just like gases, matter in plasma state has an indefinite shape and volume. What differentiates plasma from gases is the electrical conductivity. Plasma is ionized gas in which positively charged nuclei swim in a sea of freely moving dissociated electrons. The plasma state is not observed on Earth easily, but it is the most common state in the universe. On Earth, plasma can be observed in lightning, electric spark, fluorescent and neon lights. The state of matter in which a substance exists depends upon two factors. The first factor is the thermal energy, which is the energy of a body arising from the motion of its atoms or molecules, and it is a measure of the average kinetic energy of the particles. It is directly proportional to the Kelvin temperature. The second factor is the intermolecular attractive forces between the particles. The above two factors have opposing influence on the molecules of the matter. Thermal energy tends to move particles away from each other, whereas the intermolecular attractive forces tend to keep them together by minimizing the particle movement. The three states of matter, gas, liquid and solid, result from a competitive balance between the two. Thus, in the gaseous state, the thermal energy is highest and intermolecular forces are weakest. Whereas in solid state, the thermal energy is least and intermolecular forces are strongest. In the liquid state, the thermal energy and intermolecular forces are intermediate between those in other two states. Now, we can have a brief discussion on the intermolecular forces that operate in substances. Intermolecular forces are the forces of attraction and repulsion between the interacting particles, that is atoms and molecules in a gas, liquid or a molecular solid. The term intermolecular forces, however, is generally used to describe the attractive forces between molecules. These do not include the strong intermolecular chemical bond, covalent or ionic bond. So, we can examine what are the attractive and repulsive forces. Attractive intermolecular forces, also referred to as van der Waals forces. For a given pair of molecules, there may be several types of intermolecular forces at work. Attractive intermolecular forces include dipole-dipole forces, dipole-induced dipole forces and induced dipole forces, also known as dispersion forces or London forces. First one is the dipole-dipole forces, that is the attractive interaction between polar molecules. Dipole-dipole forces actually act between the molecules possessing permanent dipole moments, generally called polar molecules or dipoles. The ends of a polar molecule possess partial charges which are always less than the unit electronic charge. HCl, for example, is a polar molecule. A polar molecule interacts with neighboring molecules. Here, the positive end, that is the delta positive hydrogen end of one dipole will attract the negative end, that is the delta negative Cl end of the other dipole, so that the molecule assumes an oriented arrangement as shown in figure. Dipole-dipole forces have strength that ranges from 5 kJ to 20 kJ per mole. They are much weaker than ionic or covalent bonds. They are also weaker than the ion-ion interaction as well as ion-dipole interactions. Now, what are the factors affecting the interaction energy? The interaction energy, that is the potential energy V of the dipole-dipole interaction, depends upon the dipole moments mu1 and mu2 of the interacting dipoles. The more polar the molecule, the greater will be its magnitude. Further, it is inversely proportional to Kelvin temperature and to the 6th power of distance between the dipoles. It is given by the equation V is equal to minus 2 by 3 kT mu1 mu2 by 4 pi epsilon 0 into 1 by r raised to 6. In HCl gas, dipole-dipole interaction contribute about 15% towards the total intermolecular forces. In NO, which is weakly polar, it is estimated to be only 0.005%. In non-polar substances like nitrogen, methane, inert gases, etc., the contribution is nearly 0. The inverse relationship between dipole-dipole forces and temperature is easily understandable, as the thermal motion of the molecule tend to overcome the orienting effect of the dipoles. Thus, as the temperature is lowered, the dipole-dipole interaction increases. The magnitude of dipole-dipole forces directly influences the physical properties of substances. As a result, the greater these forces, the greater will be the melting and boiling points of substances. For example, the non-polar substances, nitrogen and oxygen, have boiling points minus 196 degrees Celsius and minus 183 degrees Celsius respectively. On the other hand, NO, which is slightly polar, has a slightly higher boiling point, minus 151 degrees Celsius, on account of the weak dipole-dipole forces present. Whereas, the more polar HCl is having greater dipole-dipole forces and still higher boiling points, minus 85 degrees Celsius. Next is the dipole-induced dipole forces. Dipole-induced dipole forces are the attractive interaction between polar molecules and non-polar molecules in a system containing polar and non-polar molecules. Here, when a polar molecule gets near a polarizable non-polar molecule, the polar molecule can induce a dipole in the polarizable non-polar molecule. That is, a polar molecule produces an electric field which can distort the electron cloud of the nearby non-polar molecule. the strength of the constituent attractive interactions depends upon the dipole moment of the polar molecule mu1 and the polarizability alpha 2 of the non-polar molecule. Then what is polarizability? The polarizability is the measure of the ease with which a molecule's electron cloud can be distorted. Molecules of larger size can be easily polarized. The greater the polarizability of the non-polar species, the greater is the strength of these attractive interactions. Here also the interaction energy, that is the potential energy V, is inversely proportional to 6th power of the distance between the two molecules r, and is given by the equation V is equal to minus mu1 square alpha 2 divided by 4 pi epsilon 0 into 1 by r raised to 6, where epsilon 0 is the permittivity of space. Induced dipole forces are present in a system consisting of HCl, which is polar, and benzene, which is non-polar, and also in a system consisting of water, which is polar, and oxygen, that is non-polar. In fact, this type of forces can be held responsible for the slight solubility of oxygen in water. Next is induced dipole forces or dispersion forces, and also known as London forces. It is the attractive interaction between atoms of non-polar molecules. Temporary variation in electronic density around atoms or molecule occur even in non-polar species. These momentary distortions in the electron distribution constantly produces instantaneous dipoles. The consequent attractive interactions between the instantaneous fluctuating dipoles produced constitute London forces. London forces generally have energies in the range 1 to 10 kJ per mole and are the weakest among the intermolecular forces. However, the actual magnitude of these dispersion forces depends upon the polarizability of the atoms or molecule. Here also the interaction energy is inversely proportional to 6th power of the distance between the two molecules. London has derived approximate equation for the potential energy V of dispersion forces using quantum mechanical calculation, and the equation is given as V is equal to minus 3 by 2 alpha 1 alpha 2 into I1 I2 divided by I1 plus I2 into 1 by r raised to 6. Here alpha 1 and alpha 2 are the respective polarizabilities of the interacting molecules, and I1 and I2 are their respective first ionization energies, and r is the distance between them. This explains the increase in melting and boiling points of the halogen upon going down the group, that is from fluorine to iodine of the periodic table. In fact, fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid under normal conditions. The presence of London forces also explains the increasing boiling point of noble gases as we move down the group. Another important intermolecular interaction is hydrogen bonding. It is a special case of dipole-dipole interaction. A hydrogen atom linked covalently to a highly electronegative atom like fluorine, oxygen or nitrogen with non-bonding electron pairs may get additionally bound by dipole-dipole attractive forces to another highly electronegative atom of the same or different molecule. This relatively weak attractive force is called hydrogen bond. That is, when a hydrogen atom is bound to a strongly electronegative atom like fluorine, oxygen or nitrogen, the partial charge separation occurs and the molecule becomes polar. The hydrogen, which is the positive end of the molecule, interact with the negative end of the neighboring molecule, forming a bridge between the two molecules. There are two types of hydrogen bonding existing between molecules. First one is the intermolecular hydrogen bonding. Hydrogen bonding present between different molecules of the same substance or different substance is called intermolecular hydrogen bonding. Intermolecular hydrogen bonding causes association of molecule into clusters. For example, association through intermolecular hydrogen bonding occurs in hydrogen fluoride. Because of the extensive forces of hydrogen bonds between molecules, hydrogen fluoride has a higher boiling point than the other hydrogen halides like HCl, HBr, Hi, containing halogens which are heavier but less electronegative. Consequently, HF is a liquid whereas HCl, HBr and Hi are gases at temperature close to room temperature. Water and ammonia are examples of other compounds that show association through extensive hydrogen bonding. Hydrogen bonding is in fact responsible for the unexpectedly high boiling point of water as compared to other group 16 hydrides and that of ammonia as compared to other group 15 hydrides. Second type of hydrogen bonding is the intramolecular hydrogen bonding. The hydrogen bonding present within the same molecule is called intramolecular hydrogen bonding. Example, intramolecular hydrogen bonding is present in salicylic acid, orthonitrophenol, etc. Next, the repulsive intermolecular forces. In addition to the intermolecular attractive forces, there exist intermolecular repulsive forces also. When two molecules are being brought towards each other, there occurs a repulsion between their electron clouds as well as between their nuclei. The magnitude of these repulsive forces increases as the distance between the molecule decreases. If they are forced to come too close to each other, the repulsive forces becomes so high that they predominate over the attractive forces, thereby stabilizing the system. Nature on its own does not create such a situation. That is why the solids and liquids are almost incompressible. In these states, the molecules are already very close to each other. Consequently, they resist further compression because this would lead to a situation where the repulsive forces are so high that the system would become unstable. Now, as we all know, water is a universal solvent and we can examine the uniqueness of water. The unique and remarkable macroscopic behavior of water arises inevitably from its nature, especially from its polarity. With two bond pairs and two lone pairs around its oxygen atom and a large electronegativity difference between the hydrogen and oxygen atoms, H2O molecule is bent and highly polar. This in turn contributes towards its ability to form intermolecular hydrogen bonds in a unique manner, each water molecule being able to engage in hydrogen bonding with 4 of its neighbors. Some of the unique properties of water includes: first one, water is an exceptionally good solvent. The great solvent power of water is the result of its polarity and exceptional hydrogen bonding ability. This is also responsible for the high specific heat and high heat of vaporization of water. Also, water shows high surface tension and high capillarity. Water has the highest boiling point and melting point among the hydrides of group 16 elements. This is again due to the presence of hydrogen bonding that we have discussed just now. Next peculiarity of water is that the density of water changes in an anomalous manner between 0 and 4 degrees Celsius. When ice melts at 0 degrees Celsius, its tetrahedral network arrangement breaks down and the freed molecule much more closely filling the space in the collapsing cavity filled solid structure, and this decreases in volume continues up to about 4 degrees Celsius. As a result, water shows its highest density at 4 degrees Celsius. With further increase in temperature, the density decreases through normal thermal expansion. In other words, water expands anomalously when it freezes. So, students, that's all about the intermolecular forces. Next session will be about the physical properties of liquids. I hope the concept we have discussed today is clear for you all. Thank you.